All right, for our second part here, we're going to talk about gas transport within the blood. And to look at this, we need to talk about gas solubility. So remember I said that we had these partial pressures, but how much of a gas was actually in there for a partial pressure was going to depend on its solubility. That is where we're coming back to now. So what you'll notice here is, first of all, there's a decline with temperature. That's important. So higher temperatures, gases are less soluble. But at every temperature that we're looking at here, carbon dioxide is much more soluble in water than oxygen, which if you think about those molecules, that shouldn't be a surprise, because oxygen is about as nonpolar as something, an oxygen molecule is as nonpolar as something can get. It's two atoms of the exact same thing connected to each other. That's a nonpolar molecule, which means it has very low solubility in water. Carbon dioxide is much more polar because it's a carbon connected to two oxygens. So there's a difference in charge there. And that dissolves much better in water. So carbon dioxide is pretty easy to transport in the blood. Dissolves in water, great, no problem, everything's fine. Oxygen is a lot harder, so we need something else to transport our oxygen. And we have, so we've got this gas exchange happening. We need to get carbon dioxide around, that's easy. We need to get oxygen around, that's harder. So how do we do that? That's where hemoglobin comes in. So hemoglobin is our oxygen transport molecule. Hemoglobin is made up of 4 heme groups, 2 alpha chains and 2 beta chains. So this is a protein. And if you remember, primary structure is the amino acid sequence. Secondary structure are these helices that you're seeing in these chains, these wrapped helical shapes. Tertiary structure is this bent shape here of a single heme group. And then quaternary structure is the fact that we have 4 heme groups all together. And each of these heme groups has an iron in the molecule, and that iron is where we're going to carry the actual oxygen. So each of those irons can carry an oxygen, and that's going to allow us to carry 4 oxygen for every hemoglobin molecule around. Now, when hemoglobin binds to oxygen, it changes shape a little bit. And so this is important because every molecule of oxygen that hemoglobin binds makes it a little easier for the next molecule to bind. And every molecule of oxygen that hemoglobin releases makes it a little easier for the next molecule to release. Now, that's our oxygen transport. Now, there's a lot more to say about this, but I'm going to glaze it a little bit because our whole POGL activity today is on hemoglobin binding, because this is actually a really complicated setup, and I want you to pay attention and look at, we're going to talk about hemoglobin binding curves and things like that. We'll talk about that a little more in the lecture, but mostly we're going to focus on that in the POGL. So the other thing that we need to talk about is carbon dioxide. I said, oh, this dissolves, it's easy. That's true. But actually, most of our carbon dioxide is transported in a chemically modified form, because carbon dioxide is actually our main buffer system in the blood. So carbon dioxide dissociates and produces a hydrogen ion and carbonate, and can also dissociate again to produce carbonic acid. And so this back and forth shift provides a buffering effect for different acids. However, that also means that carbon dioxide produces these hydrogen ions and makes the blood more acidic. We're going to talk about this a lot more next week when we get to pH regulation in the body. Now, the other thing that happens with carbon dioxide is that some of it is actually also carried by the hemoglobin. So we have some is dissolved, most of it's chemically modified, and some of it's carried by hemoglobin. And that's important because hemoglobin is really affected, its binding to oxygen is affected both by carrying carbon dioxide directly and by the pH. So when there's high carbon dioxide, it's going to lower the pH, which makes hemoglobin less attractive to oxygen. Now that's actually really useful to us because it means that when there's a lot of carbon dioxide in the blood, that lowers the pH, and that causes oxygen to be released. So where would you find a lot of carbon dioxide? Generally at those metabolically active tissues. So if you're at a metabolically active tissue, it's producing a lot of carbon dioxide, it's going to lower the pH, which is going to cause more oxygen to be released where we need it, at those metabolically active tissues. If there's a high pH, which means a low carbon dioxide, then you're not releasing that extra oxygen. Similarly, if carbon dioxide itself is bound, that's also going to make hemoglobin less attractive to oxygen. So the more carbon dioxide that binds, the more oxygen that gets released. Now, the other thing that we have here is the different types of hemoglobin. So we have fetal hemoglobin and adult hemoglobin. And fetal hemoglobin is more attractive to oxygen. And that is important because oxygen needs to flow from the maternal hemoglobin to the fetal hemoglobin. So the only way that that can work is by fetal hemoglobin taking oxygen away from the maternal hemoglobin, which means that for the fetus to get enough oxygen, it needs to have hemoglobin that is more attractive to oxygen than the maternal hemoglobin. Now, the other thing that we get into here is regulation of ventilation. So I've talked about a few different things here with this carbon dioxide and pH. Now, that's where this is going to come in. Now, you know that you have some direct voluntary control over ventilation. So, if you take a big deep breath, obviously you had control to do that. The fact that I'm talking, I'm controlling my breathing. But if you're just sitting at rest and breathing normally, it's all these other factors that are coming into play. So there's emotional stimuli. You already know that if you're stressed or anxious, your breathing is going to speed up. That's through the limbic system. Then we have these chemoreceptors. Now, we have central chemoreceptors and peripheral chemoreceptors. Central chemoreceptors are located in the brain itself, and they primarily respond to pH. Some of them also respond to carbon dioxide. Now, of course, increased carbon dioxide is going to decrease pH. So either way, that increased carbon dioxide or that decreased pH is going to cause those chemoreceptors to signal to increase the breathing rate. The peripheral chemoreceptors are similar. You're going to find those primarily in the aorta and the heart, and those respond to carbon dioxide and to pH, as we discussed. There are also chemoreceptors that respond to oxygen, but in general, those are not the main ones that we rely on. So those only come up in fairly unusual circumstances. This can come up in, for example, situations where the partial pressure of oxygen is lower than normal, like a high altitude environment, or any situation where oxygen is depleted. We also have responses to stretch receptors in the lungs, saying that the lungs are too stretched out, and also proprioceptors in muscles and joint, where we know that there's activity going that's already going to upregulate breathing, just because you're starting to move, even before you start getting signals saying that you need that oxygen, or that you're producing too much carbon dioxide. All right, so that's sort of our general summary here. And as I said, we're brushing over hemoglobin quite a bit because you're going to focus on that in the POGIL. Now, Oh, sorry, this still talks about a short case study. I eliminated that for this semester, so don't worry about that right now. But so the POGO has been posted. I encourage you, as always, to do that if your with your groups if possible, but it's also fine if you're doing it on your own. And if you have any questions, you know how to find me. All right, be well and good luck with the POGO.